Hello, I'm Tom Watson. I work at IBM. I'm also the project lead of the Equinox project at Eclipse, which is responsible for implementing core specifications of OSGI. Primary example is the OSGI framework itself. It's a reference implementation. And today I'm here to talk to you about the subsystem specification, which is going to be included in the R5 Enterprise specification. Now, I was actually looking at my involvement in the specification. It's been a rather long process. And I believe it was 2009 I gave a presentation along with Richard Hall on a thing called Composite Bundles. So this was RC138. We were proposing adding some new core concepts, particularly this thing called a composite bundle, which was basically a bundle that could be composed out of other bundles. So a way of grouping bundles together and providing a level of isolation and then specifying what you import into the composite and export out. Then in 2010, I also gave another presentation on composite bundles. It was the new and improved direction that we were taking. We still hadn't released a specification for it, but we thought we had a better design. I gave another presentation, and I actually had code and demos and stuff. But then in the summer of 2010, we actually went in a drastically different direction, decided that composite bundles really didn't belong in the core. Instead, we added these hooks, resolver hooks, bundle hooks, and we're using the service hooks that were already available from R4.2 in order to enable isolation policies, if you will, or isolation layers above the framework altogether, so that we didn't have to ingrain a particular policy in the framework. We could let people devise their own collections of bundles and decide how they're going to actually do the isolation. So that's where we're at. We're at in 2010 and beyond, and we left the rest of the stuff to the subsystem specification in the enterprise, and that's now what's being released in the public draft just this week. And it includes the subsystem specification that I'll be talking about right now. So, first thing I want to talk about is the motivation. Why did we decide we need to have this specification? In the enterprise space, there's actually a lot of examples of this concept of a collection of bundles. On the server side, they really would like to be able to deploy a set of bundles, be able to manage it, maybe activate them all together, uninstall them even altogether. Basically, a coarser grain level of deployment. And there's several examples of this. Apache Aries has a notion of applications, which are kind of fully isolated things that they install. Apache Drama has a similar concept of their applications, but they're actually unscoped. But you share a lot of the same concepts and metadata of Apache Aries. It actually is based on Apache Aries. Apache Karaf also has this notion of features which are unscoped. Eclipse Virgo also has their plans and pars, which can also be considered scoped or unscoped. WebSphere has both applications, which are much like Apache Aries, and also this concept of composites, which are isolated but also can export and make certain things available to others to use. And GlassFish has their applications, and Primus has systems, which are also just groups of bundles that are not really scoped or isolated. So it's kind of crying out for this standardization so that we can give developers a common thing to program against and develop against and have portability across these different environments. And also be able to provide some common tooling and perhaps an ecosystem where we can have these subsystems that are similar to bundles. They're artifacts that can be reused and perhaps available in repositories for reuse within different systems and environments. so now I'll go kind of into the model of what subsystems are. The model itself, the subsystems form a hierarchy. So at the very, depending on how you draw it, if you put the root at the top or at the bottom, but the root is where everything starts. All other subsystems have one or more children. So the root is basically the ancestor of all the subsystems installed. And subsystems can have many children, as many that get installed along into it. And then there's this concept. So then there's this concept of a region, and the region is what actually provides the isolation. So a region kind of encapsulates a group of one or more subsystems and isolates them from the other subsystems that are installed. So what does this mean for bundles when they're trying to import and export capabilities from another? In a standard OSGI framework, if you have, like in this example, bundles A and B installed, they're freely able to export and import a capability. So in this example, I just have two simple bundles. One's exporting the Y capability, another's importing it. So I'm talking at the generic level. A capability might be a package or a service, or a requirement might actually be require bundle and so on. So in a flat framework, these are able to get wired up. In subsystems, depending on if they're scoped or not, may actually prevent that from happening. So these two subsystems, if they're scoped subsystems, this kind of wiring between them can't happen by default. The regions around them put up the wall. But subsystems are able to selectively export. So maybe subsystem 2 here wants to make the capability Y available. And the way they make them available to their parent. And then other children of that subsystem can also selectively import the capabilities. So now we allow for that wiring to happen. Unscoped subsystems are a bit different. They always exist in the context of another region. So in this particular case, I have the unscoped subsystem Y, U, that's a child of S1. It actually becomes part of that region. And since they're completely unscoped, they're able to share resources with everything else within that subsystem. One way I think of this, and others don't actually like this analogy, but I think it fits quite nicely, is if you're familiar with fragments. I kind of think of the features as being fragments to the scope subsystem within the region they're contained in, because they are conceptually adding content to that region, and the scope subsystem has visibility into the capabilities of the unscoped, and vice versa. The unscoped can actually see everything that's from the scope subsystem, so it's kind of like it's host. So there are three basic types of subsystems. The first one being features, which is what I was just mentioning on the last chart, are unscoped. So in this particular case, we have 4 bundles, and we want to group some of them together into logical units. So in this particular case, we're going to say A and B belong together, and they provide some functionality, and I'm going to call that feature F1. And similarly, C and D provide some functionality, and I want to group them together and have them have a shared life cycle. So when I install F1, I'm going to get A and B. And also if I uninstall, they're going to be uninstalled, and and six, basically across the board, start and stop. They can have children. It's not really necessarily that useful because everything gets into this same space, so there's no scoping, but children basically are a way of even componentizing the feature further, but conceptually, I mean, it's as if you put that bundle F up into F1. Like I said, they're unscoped, so they're freely able to share capabilities with one another. The other thing to point out is that the bundles, like here we have E that is actually a duplicate bundle between F1 and F2, and whenever both of these features are installed within the same context, they actually share the physical same bundle at runtime. So that E bundle is not installed multiple times. And finally, features have to be contained within a region. And the reason this is because the root region is actually considered a scoped subsystem. So if you install a feature as a child of the root, then it's going to become part of the root. So some examples of what I was mentioning before out there already, Karaf features and Virgo and scope plans closely match the feature model. The next type is what we call composites. So this is a coarse-grained subassembly module. And what I mean by that is you're kind of defining this module that advertises what it actually explicitly imports and what it exports. So, similar to how a bundle expresses what it exports and imports, this does as well. But what is actually providing it on the inside is kind of implementation detail. You don't necessarily care or need to know what's inside of there that it's actually requiring Y or F, providing X. And when they're installed, in this particular example, they're children of root. They're able to explicitly export and import the resources, and then get wired up through their parent. But in reality, they are just composed of resources, most commonly probably composed of bundles. So here we just have these bundles in here, and they're the things that are actually providing it, but they're encompassed in this unit. They're fully scoped, in contrast to features, if both of these contain the identical bundle E, that's going to result in actually two different installations of that bundle within the runtime, two distinct implementations. So even if they have the same symbolic name and version, there'll actually be two different installations of them at runtime. So some examples of this, the old design I was talking about that I gave talks on years ago, RC138, kind of models that approach. Also, WebSphere Composite Bundles, what they're offering there is similar to this type. The last type is applications. So this is what would be used for composing hosted applications. For example, on an application server, or a J2E server, using again resources or bundles. So they're also fully scoped like composites. So you can have these duplicate resources that are implementation details of the applications, but they don't want to share them. They need their own copies for one reason or another. But they're also able, at runtime, actually what happens is that the content is put through a resolution step so we can figure out what external dependencies this thing has that aren't available within the resources in it. So in this particular case, these bundles A and C need this capability X, which actually can be provided by a resource from the root. So, we say the import policy is implicit in that the application doesn't actually state it imports those. Those are calculated at runtime based on the dependencies that are not satisfied by the content bundles. And some examples, again, the Aries application are scoped, Virgo scoped plans and PARs as well. And so you can mix and match these things within the same environment. This particular example just shows, we have this composite that's actually composed of two different features, and it's providing, a platform basically that allow applications to be installed on that they can import various capabilities from. Next, I go into some of the metadata. So the metadata that describe the composite definition, the subsystem definition is it's roughly speaking a manifest format. It has some relaxed rules, but just think of it as the manifest format, and it's in the file OSGI subsystem.mf. There are some headers that you put in this file that are unique to the subsystem type. In particular, it's the ones dealing with composites because it has explicit imports and exports. So there are explicit sharing headers that go in there, like import package, export package, that can only exist in a composite. But all the other concepts are common across the types and use the same headers within the subsystem manifest. And the headers cover the identity and type, content, sharing policy, and some human readable information. So if we go into the details, it's identified by a symbolic name and version. So similar to a bundle, this is intended to be assigned by the developer whenever they're developing a subsystem. They're getting a group of bundles together, and they want to version it and name it. So they give it a symbolic name and version. The next bit of metadata is the subsystem type. So this is just indicating whether it's an application, a composite, or a feature. There is one directive on this header that actually specifies what we call provision policy. And this is just indicating an indication of where you want your dependencies to be installed. By default, the dependencies get installed into the root subsystem, but you can actually specify your own subsystem as the place where you want your dependencies to be installed, which is what that directive is used for. The next bit of metadata is for the content. So this is where we actually identify what resources is a particular subsystem composed of. And again, it's identified by a symbolic name and version range, and also a type. So there's a set of standard types the specification has, which of course is bundle and fragment, but also the OSGI types, the subsystem types. So a subsystem can actually be composed of other subsystems. This header actually can be optional. You can instead just include the resources within the archive itself, and then the subsystems implementation will use those resources as the content, and you don't have to actually specify them in the subsystem content header. And I also should mention if it is also actually possible to install an empty subsystem. Not really that useful, but there is introspective APIs to where you can install a bundle into a subsystem. So you might set up a sandbox that's an empty subsystem and then be able to install bundles into it dynamically. The next bit of metadata is the explicit sharing. For this only applies to composite bundles. So we reuse many of the existing bundle headers where applicable. So import package, export package, require bundle. Also the headers for require and provide capability from R43 core specification. but we also have these other two additional headers for importing and exporting of services. And finally, you just have a couple informational headers for the name and the description. So portability of the metadata. I haven't really gone into deployment manifests, and I won't be going into it right for this presentation. But the subsystem manifest is portable to a certain degree, but we have a standard set of types that are supported, bundles, fragments, and the 5 minutes. And so subsystem implementation can support additional types. So if you include those kind of types in your metadata, then obviously it can only be installed on that implementation that supports that. Also, the service dependencies, the implementation has to support the metadata you're using for that. So like if you use Blueprint, then you better make sure your subsystems implementation understands a Blueprint to know what bundles provide and require services or declarative services, IPOJO and whatnot. Packaging is just a zip file. The standard extension is ESA. It includes the 2 bits of metadata, and like I said, it optionally can include the resources themselves, but it is just a standard zip file. Runtime, the API for installing a subsystem is a subsystem service. So when the subsystems implementation is first started up and there is no subsystems installed, by default there is a root subsystem that basically represents the currently running framework. And then you use that to install any child subsystems. And each subsystem that gets installed gets its own subsystem service registered with the service registry, so you can discover what subsystems are installed. You can get their services and enact the lifecycle management operations for starting and stopping and so on. I'll try to go over some of the actual operations here, but we're running short on time. So it's quickly just going through what an install operation actually involves. So if I want to install my first subsystem, I'll use the root subsystem call install, and you provide the input stream to an ESA file. And that starts off this installing process. So we're installing an application A1. It's in the installing state. The subsystems implementation is discovering what content is included in that subsystem. So this can be repository based. So it just reads the subsystem content, figures out what from the symbolic name and version ranges and types, figures out what resources it needs to install. So I can get those from the repository service that's also included in R5 in order to discover the actual resources. In this particular case, this application is made up of A and B, so it gets those bundles installed. The next kind of step in the installing process is to ensure those resources can be resolved at runtime. And in this particular case, it discovered that they have these dependencies for these capabilities that can be provided by bundles E and F. So it determines that in order to get this subsystem to install and actually be functional, I need to provision E and F into the root. And then that makes it into the resolved state. If I install a second subsystem, they can share capabilities. So if C here needs the same capability that A did, they can share that capability provided by that common resource F. The next operation is start. So I need to get these bundles started in a controlled manner. So I just start the subsystem. The first thing that happens is that the dependencies that are referenced by the subsystem actually get started. And then the content bundle gets started. and optionally you can control the order that the individual resources within the subsystem get started. If I start the second subsystem, it does the same thing. You'll notice that these two subsystems share the same bundle F, and since it was already active, it doesn't like reactivate it. It just checks that it's active and makes sure that it is when it remains active when A2 is activated. Stop is the next step, and as you might predict, it's pretty much the opposite of start. So it stops the content bundles, and then any resources referenced. In this particular case, F is still referenced by this active subsystem A2, so it doesn't stop it when you stop A1. But if I stop A2, then it's going to stop the rest of the resources. Finally, we have uninstall, and predictably, it's got the same pattern. It's going to uninstall the content bundles and the referenced dependencies. It didn't uninstall F because it's actually being used by a subsystem that's still installed. You uninstall A2, and that's going to get rid of the rest of the resources. So that was the end of my presentation. I don't need to go over the summary. I think I'd rather see if there's any questions. Are we completely out of time?
You can take questions.
Sure.
Services. Are the services scoped?
Yes.
And by saying export service, you basically punch it through the scope and give everybody else access to that service.
That's right. It's just the same as if you export a package, then you're going to make that package available.
You just come on, disconnect.
Right. Any other questions?
I just wanted to say you didn't cover applications, which I thought had taught us. I think you only covered composites and features. It might be worth saying in one sentence what an application is.
Did I not cover applications?
No.
Okay, I hope it's only you that missed that. Did everybody else saw that, right?
I think you missed features as well, didn't you?
Did I miss that?
No, you missed the
Can I
features.
Can I start
I
over?
think you missed subsystems.
That's. I covered composite bundles, though, right?
Yes,
Yeah.
yes.
Anything else? Okay, thank you.